Good morning, good afternoon, and good evening, everyone. So, today we're going to be continuing our linear algebra series, and we're going to be talking about matrix algebra, right? So, basically, we already know what algebra is, right? When we're doing it with real numbers, right? So, what we're going to do next is how do we do the algebra with matrices? So, that's really all there is to it, okay? So, get started, let's consider a hypothetical natural food store that sells organic chicken eggs that come from two suppliers. So here is the Happy Coo and the Expeditious, right? And here they sell a bunch of eggs, basically. So each of these suppliers, well, they provide two types of eggs, which are white and brown, in medium, large, and extra large sizes. And the store's current inventory of 12 egg cartons is given in table 1, which is this one, right? And we can actually translate this type of information into matrices, which we've done in the past. So for Happy Coup, we translated it into a 3 by 2 matrix, and same goes for Expeditious. And we could add these two matrices together to get the total number of both white and brown eggs and their corresponding sizes. So here we see we have a total of 13 medium white eggs, a total of 8 medium brown eggs, a total of 14 large white eggs, a total of 12 large brown eggs, and so on and so forth. Okay, so we can do that. Another thing we can do is multiply the matrix by a scalar, right? And so the way that works is we just multiply it by a scalar, and what happens is we multiply that particular number to each element of the matrix that we're multiplying the scalar with. Okay, that was a bit confusing. Basically, we multiply it to each element, the number, okay? And if we do that, say in this case 12e, right? We're multiplying 12 to each of the elements in E, and this would give us a resulting matrix of 96, 36. Okay, trying to speed this up a bit. 96, 60, 72, and 120, right? So that's going to be the resulting matrix from that operation. And here we have a buzzword called equal matrices. So these computations illustrate addition and scalar multiplication of matrices, and they are analogous to those of vectors. And so as these operations suggest, two matrices are equal if they have the same dimensions and if their corresponding entries are equal. So this is what we mean by that. So we say two matrices are equal if they have same dimensions. So that means they have the same number of rows and columns, and corresponding entries are equal. So they have the same entries or elements in the matrix, which I think is pretty self-explanatory. Okay, so we just went over two concepts here in this definition. So I'm gonna write down the definition. So we say, let C be a scalar, and we let A be a matrix with I think this is n by m. So we do 1, 1, all the way to n1. And then we keep going here. 1, 2, all the way to 1m. We go down here and m to, actually we can do this. That's fine. Okay. So that's the matrix A. Then we also have matrix B. Here we'll call it, well, we'll call it B. And we say this has the same number of dimensions as A. So you do 1m, nm, and 1, right? So these two matrices have the same dimensions. So these are n by m. So we say we have addition and scalar multiplication are defined as follows. So here, again, we look at a couple of buzzwords. We look at addition, and we look at scalar multiplication. So what do we see for, let's say, addition, right? So let's say we do the matrix, or we add those two matrices together, A plus B. So in theory, what that's going to look like is we add their corresponding elements, and we just keep doing that. N by 1 plus B n by 1, and we keep going, right? So what that's gonna, okay, let me just finish it. This is 1m. I keep going here. And m. Right? So we just add their corresponding entries together. That's addition. Now, scalar multiplication. So for instance, that's some scalar C. We multiply it by some matrix A, and what that's going to look like is we just multiply that scalar to all of the elements. So n by 1, n by, no, 1 by m, n by m. Okay? So those are the two ideas that we've gone over so far. Let's actually try one example here. Okay. So here let's see. We let A be, or we let A have, okay, A is a 3 by 2 in this case. And B is another matrix, 3, 5, 0, negative 1, 0, 2. And what we want to do is we want to find 3A minus, oh no, 3A and A minus 2B. So when we do 3A, this is an example of a scalar multiplication, right? So we multiply 3, this matrix here. We could do this by hand, or we could do this in code. But this should give me 12, 6, 21, -3, -9, 0. So that's what that should give me. Now to get a minus 2b, so again, we just write down the matrices. So this is matrix A minus 2 of matrix D, which has entries 3, 5, 0, -1, 0, 2. And then we just solve it, right? So we get, okay, maybe I'll solve the scalar one first. So it follows the same thing as PEM does for real numbers, but here we're just doing it for vectors. Or no, for matrices, my bad. 0, 2. And then I think we could an addition, so we just put the negatives here. One becomes a positive. These are negatives. And we should get 4 minus 6, -2, 2 minus 10, -8, 7 minus 0, 0, -1 plus 2, 1, -3 plus 0, -3, 0 plus -2 is -2. So that's the resulting matrix of A minus 2B. I hope I got that one. Oh, shoot. I messed up somewhere. Oh, I forgot to multiply the 2 here. My bad. So this is a 4. So this here is a 4. And that should be it. Cool. And we also have different kinds of properties that follow for matrices, similar to vectors, right? So, okay, let's suppose RST are real numbers. So we say they belong in the real number solution set, set of real numbers. And here are the laws of arithmetic. So we recall arithmetic laws. And these are elementary stuff, right? So here we have the commutative property. So what that means, real numbers, right, is if we add R and S, that's the same thing as adding S and R. So we call this the commutative property. Okay. We also have associative properties. So no matter the order in which you add these real numbers together, they're the same no matter what. So this is what we call associative property. Then we also have distributive property. So when we distribute, so these are all some stuff that we know in lower level math. And then we have additive identity, which is just R plus a 0, which is the same thing. So we call this the additive identity. And apparently we also have these laws in matrices, right? So let me actually do that. Okay, I put all of the theorems here. So I'm probably just gonna put this one here. Okay, this one's in 5. Oh, I'll put this definition there. Oh shoot, I already went to the example. Cool. This should be over here. Okay, agrees. That's nice. Let's see. So we have these arithmetic properties, right? Now let's look at the theorem. 3.11. So again, we let S and T be scalars. A, B, C be matrices, or in this case, N by M matrices. And we also have a 0 and M, and we say this is an N by M matrix. Okay, let me actually write this. So S and T are scalars. A, B, C are N by M. 0 and M is also an N by M with all 0 entries. So those are our givens. Then we have the following properties. So in this case, we have the commutative property. So when we add two matrices A, B, that's the same as adding B and A. B first, then A. We have, oh no, that was commutative property. We have distributive property, where we have some scalar multiplied to the sum of both matrices is the same as multiplying each matrix first by that scalar, then adding. So that's the same thing. We also have this property where it's also distributive, but we have the sum of two scalars multiplied by a matrix is the same as multiplying those scalars to that matrix, then adding them. And then we also have another property where we add two matrices first, and then we add it to some third matrix, which is the same thing as adding B and C first, and then adding it to A. Same idea as associative property. And then we also have this property where we multiply two scalars together, then multiply that to some matrix, which is the same thing apparently as first multiplying the matrix by a scalar, and then we multiply to another scalar. And then lastly, we even have some matrix A added to 0 matrix, which is the same thing. So this we call the additive identity. So we have some very, very similar ideas from arithmetic laws that we can apply to matrices, and that's good, because then we won't be so confused as to memorize so many theorems, right? At least it's a healthy kind of thing. We're not we're not looking at too much stuff. But why is this not working? Okay, it's not loading. It's funny. Let's see. Or maybe I put too much theorems that's confused. Okay. Okay, let's continue. So we have a proof for each of these. I'm not going to go through the proof anymore, but it's really just going through each of them and trying to see how we can relate it to the other, right? So that's how proof goes. Okay. Now let's actually extend the definition of this idea of matrix multiplication. So what is this idea? So it's actually extending the definition of multiplying a matrix times a vector. So we're going to extend that idea. So far we've been doing addition of two matrices and we multiply a matrix by a scalar, but here we're going to try multiplying two matrices together. But first we have to do it by multiplying a matrix by a vector. So to do that, say we have, okay, let me do it like this. So say we have A, which is a matrix, right? I'm going to assume, actually I don't see. Yeah, I don't see what dimensions of A are going to be. So I'm going to go with what the book is saying. So we say A is a matrix multiplied by some vector X. So this is equal to, so we have a bunch of vectors all the way to some K. And we multiply that by a column vector, which also goes to K, obviously, right? Reason being is we need the columns of A to be the same as the rows of that vector X. So we have X sub 1, A sub 1. And what do we notice about this idea? It's actually a linear combination, right? Believe it or not. We're multiplying each vector by a scalar, but also we can say from calculus 3, this is a dot product of two vectors. So we could go with that idea, right? So, okay, so we say this product, so this is actually a vector. The product AX, we say is defined, or in other words, it works, right? So it's defined as long as the number of columns of A are equal to number of rows of our vector X of components. Not necessarily number of rows, number of components. I think it would be a better fit to say that. Okay. Great. Now let's try, we let B be a matrix with these vectors. I think this goes all the way to M. So we can think about a matrix as a column of vectors. It has column vectors from 1 to M. So these have M vectors. B has M vectors. We say that these guys, B sub 1 all the way to M, say they have K components. So from there, we know that B has K number of rows and M number of columns. So we say that this is K by M. Okay? That's what B is to describe its dimensions. So what now? Then let's go back to that matrix A. We say that A, B1, maybe we go to AB2, why not? All the way to some BK. Oh, they put K here, but it's all right. are all defined, right? With each having the same number of components as A has rows. So we say that each of these, so these are vectors. When you multiply a matrix by a vector, it's going to be a vector. So these vectors are all defined, while each of these vectors have the same number of components as A has rows, right? So these vectors are all defined. Okay, with each of these vectors having same number of components as A. So we say that A has K components, or in this case, K vectors, while these guys also have K components. Okay. Cool, let's look at the definition here. So here's the formal definition, I'm going to say. So this definition tells us that we let, in matrix multiplication, we let A be an n by k matrix, and B, say, is equal to a column of vectors B1 all the way to M, and we say this guy is a K by M matrix. So we define the product of these two matrices So we say product is AB, which is the same as AB sub 1 all the way to AB sub n. Okay? So here we're actually multiplying the matrix A to each of the vectors of B. That's what we're doing. So when we do that, we're actually going to get an n by m matrix. That's what's going to happen. So we're going to get another matrix when we multiply two matrices. Okay? This thing's taking a while to load. Taking a while to, yeah. Okay, nice. Great. Now let's look at another example here. I think I can do a couple of examples from the skill set, but we'll see. Example 2. So here we let A be a 2 by 2 matrix with these elements. B is also, no, B is a 2 by 3 matrix with these elements. Okay. And the idea is we want to multiply these two. So we find, so if they exist, AB and BA. So how do we find AB? Well, first we have to check, right? The number of columns of A should be equal to the number of rows of B. So is that true? Are the number of columns of A equal to the number of rows of B? That is true, right? So here actually we say A is a 2 by 2 matrix while B is a 2 by 3. So AB is going to be a matrix of 2 by 3. And it exists. So AB exists. So how do we actually do the thing? How do we do this? Well, based on the definition, we're going to multiply A to each vector of B. So how do we do that? Okay, let's start. Let's start multiplying. So we do 3 times -1 plus 1 times 4. That's one of them, right? And now the next one we say is -2 times -1 plus 0 times 4. So this here is going to result in A B sub 1. And that B sub 1 is a vector. Okay. Then we keep going. So we say 3 times 0 plus 1 times -3. So this is A times B sub 2 vector. Then we keep going. -2 times 0 plus 0 times -3, which is actually just a 0. And then we keep going. So we do 3 times 2 plus 1 times -1, -2 times 2 plus 0 times -1. And that's actually just a number, or no, a matrix. So here we say we get 1. We got 2 by 3. 1, 2, -3, 0, 5, -4. Now you guys can check, see if that's right. 1, 2, 0, -3, 6 minus 1, 5, -4. Yeah, looks right to me. And we're done. So that's AB. Now we look at BA. Now BA, so what this is trying to tell us, or what we want to happen, is that the number of columns of B should be the same as the number of columns of A. But that's not true. It does not exist. Since columns of B. So I think there's a way to write this. Column of B is not equal to row of A. They have to be equal. Okay? This thing, or this guy, doesn't exist. So actually, we say that AB is not the same as BA. So this idea of multiplication does not work for matrices, right? At least that's what that's trying to prove. Okay, let me see if I can go through some, maybe not all, but some examples. Hopefully, skills. Let's try a bit. Hopefully, if it works. Okay, let's go through this. If we get it, cool. If we don't, maybe we haven't discussed it yet. Right, so we let A be that. Now here we can see A is a 3 by 3 matrix. The identity matrix is also a 3 by 3. So this is just 1, 1, 1. That's the identity matrix in and of itself. Now what's 3i minus a? So the way I'm going to do that is 3 times that identity matrix minus a. 3, 2, 0, 1, negative 1, 2. I'm writing it by row. Last time I was writing it by column. So here we got 3, 3, 3 minus 3, 2, 0, 1, negative 1, 2, 0, 4, 2. And from there, we just apply the corresponding entries of each matrix. So 3 minus 3, 0 minus 2, 0 minus 0, 0 minus 1, 3 minus negative 1, 3 plus 1 is 4, 0 minus 2, 0 minus 0, 0 minus 4, 3 minus 2 is 1. And that's the answer. So I would just put these in 0, negative 2, 0, negative 1, 4, negative 2, 0, negative 4, 1. Right? That's what I would put. Let's see if we got that. Put 0 there, negative 2 there, 0 there. So I'm putting them row by row. Negative 1, 4, negative 2, 0, negative 4, negative 1, and I think that should be good. Nice. Okay, we have a couple of answers. Okay, we have a couple of them that I haven't tried yet. Okay, because we even have transpose here, which we haven't discussed. I know what it is, but we haven't discussed it. So I'm gonna get ahead of myself here. We have some matrix multiplications, and we also have linear transformation. So I think that one's pretty exciting, but we'll see. Okay, so let's go through question 3, which is another type of multiplication of matrices. So to do d plus r, right, you just go through the matrix, add the corresponding entries together, we should get them, right? So here, in this case, we get 6, 0, 0, 2, and we're done. That one was pretty easy. 6, 0, 0, 2. Now you just, okay, now I have to do this part. Okay, let's do dr. So here again, we just multiply the matrices. But I think I probably know what's going to happen. 2 times 4 plus 0 times 0, 0 times 4 plus 3 times 0, 2 times 0 plus 0 times negative 1, 0 times 0 plus 3 times negative 1, and we should get 8, 0, 0, negative 3. And we're done. Like work. Let's see. 8, 0, or my other values, 0, negative 3. Now we check and we got them. Nice. And I think we can also do question 4. So I'm actually skipping steps here. I'm not going through each question chronologically. I'm just seeing what I can do now so that I can get it out of the way. Right. So let's do question 4. So here we actually see, okay, we have two matrices again. We just do the same thing. Now let's actually check. Are the columns of A equal to the rows of B? True. So we know they exist, right? Okay. Now I think I can do this. Just 3. Okay, let's try. So 1 times 1 is 1. 3 times 2 is 6. 0. So this is 7. They immediately add them together. And then here we have negative 1 times 1 is... Oh, wait a minute. What do I do? Here. Okay. Negative 1 times 1 is 1 plus 4 minus 2. 6. 5. Oh, 1 plus 4 is 5 minus 2 is 3. So this here is a 3. So we did this, did this. Wait a minute. Wait, what was it supposed to? Oh, shoot. Wait, so this was a 2 by 3. There's actually a trick here. Then B is, I believe, a 3 by 2. So, oh, it's going to be a 2 by 2 matrix. So this B is going to be a 2 by 2. Oh, yeah, there we see it. So we have 7, 3, and we keep going. So here we have negative 1 plus 15. Oh, that's it. So here we have 14. Negative 1 plus 15 is 14. Next, we have 1 plus 10 plus 3, 14 as well. And there we have it. That's AB to that matrix. 7, 3, 14, 14. Oh, messed up one part. The 3, what I messed up on? This is negative 1 times 1, 2 times 2, 1 times negative 2. What's that? Same thing as negative 1 plus 4 minus 2. 3 minus, oh, it's a 1. This thing's a 1. Okay, great. Let's see if we got it. I change this to a 1. Nice. Okay. Right, so I'm gonna continue this. Wait a minute. Yeah, I'll stop this for now. I'll continue this in the next video, but I hope you guys enjoyed and learned something, and I'll see you all in the next one.